Okay, so getting started with our 11-3 notes. Today is the 2nd? Yes, 2nd of June. We've already glued down our figure that we're going to refer to. It's going to help us better understand what the parts of the polygons are. We've got in this section 11-3, we're going to be finding of areas of polygons. And we've messed around with areas before. We've messed around with areas of squares and triangles. Square is side square. A triangle's area is 1.5 times the base times the height. I'm just trying to remember the ones that we've warmed up with. The area of a rectangle is length times width. We even messed around with a trapezoid area formula. 1/2 times the base. No, 1/2 times the height. And then you multiply that by the sum of the bases. So we've got some polygon stuff going on, but the fact of the matter is that all of our formulas go up to polygons that are side length of 4. So we're going to be messing around with, actually, I'm going to write this, side lengths that are greater than 4. So if we've got to find the area of something that's bigger than a quadrilateral or a triangle, we're going to have to go into using some different strategies. Now, the very first thing is the center of a regular polygon. The center, it kind of sounds silly to even say this. Now, first of all, regular means that it has all same sides and angles. And I think probably the best thing for us to do about center is just refer to the figure. The P is the center in our figure. So we're going to use, and I'm talking about right in the one that we glued on, P is the center. Regular means that it has the same sides and angles. Now, the radius of a polygon goes from the radius of a polygon goes from the center to a vertex. And I want you to pick up one of your colored pencils and highlight the P to N radius. And even in the picture, they say, see, there's the radius, P to N. So it goes from a center to one of the vertices. Now, mind you, the radius could be all through this figure. I could draw a radius from P to any of the vertices, but the one we're going to refer to right here is going to be the P to N. I'm going to use my same colored pencil, and I'm going to just put P to N up here. I'm going to use my same colored pencil and put P to N up here. Now, this whole, what do we got here? This is a hexagon, and this hexagon, let me just describe this figure for you. This is a hexagon, 6 sides, inscribed in a circle. A hexagon inscribed in a circle. So we're going to be messing around with finding the area of figures like a hexagon, and we're just using this as an example to lay the foundation with the measures that we need. Now, the apothem. This is a weird one. The apothem of a regular triangle. The apothem of a regular triangle, and I'm looking up on the top of page 611. The distance from the center to any side of a regular polygon is called an apothem. The distance from the center to any side of a regular polygon. The apothem. And I'm actually going to grab my other colored pencil. We got a good little tune kicking in the background here. Can you guys hear it? It's a wild thing. You hear it? You hear it? P to Q is the apothem. Now, just a couple of things. The apothem, there's that word again. The apothem is P to Q. So I just got my colored pencil kind of, sort of highlighting the vocabulary right along with the colors. I didn't want to draw this. That's why I had you guys glue it. I thought if we drew it, it might get a little weird. Now, when it says to any side of a regular polygon, it's going to be the shortest distance, and it goes to, I'm going to put goes to the midpoint of the side. It goes to the midpoint of a side. Funny, I'm giggling about this song in the background. So right now your two different colors just went along with the radius and the apothem. Now, do you guys see how they name in our little picture here? They name MPN as what they call a central angle. M to P to N. Do you see how they go along and name this as a central angle? And a central angle is an angle formed. A central angle is an angle formed by two radii. That's plural for radius. An angle formed by two radii drawn to consecutive vertices. Now, consecutive, remember, means that they're next to each other. An angle formed by two radii drawn to consecutive vertices. An angle formed by two radii drawn to consecutive vertices. Now, there's another little concept that goes on here. So, you guys see how this, now they're talking about like P to M is a radii, just like P to N was, and they were referring to this central angle that's going on here. And I don't want you to highlight or anything, I just want you to kind of see it. Now, if you guys notice here, this is one of, like, let's consider this to be like a piece of the pizza or a piece of the pie. How many are there that are just like this? How many triangles are there just like this within this hexagon? This one's sitting here. There'd be another one. You see I'm just kind of lightly doing it in my pencil. So 1, 2, 3, 4, 5, 6. No, not the little ones, this bigger piece of the pie. You see what I mean now? All right, so the central angle of a regular polygon, its measure is equal to 360 divided by the number of sides. So like, what's a central angle in this polygon here? It would be 60, because there are 6 of these same size triangles that are outlined by PM and PN. And so here the central angle's measure would be equal to 60 degrees. If it was 8-sided, we'd have like 8 little, I don't know, pieces of pizza, pieces of the pie. And you divide it by whatever the number of sides were. So that kind of lays the foundation. We'll be looking back at some of this as we go into the formulas and whatnot, but let's go down to area formula for a rhombus and a kite. Area formula for a rhombus and a kite. I'd like to just drop in a couple examples here. Do you guys see what we've got going on? Why are they using the letter D? What do you think about the letter D? Why are these considered to be the letter Ds? Don't get all silly, you teenagers. What's it doing going through the figure? The word's there. It has to do with diagonals. So now the other thing that I want to point out to you guys is that they go and measure these diagonals and they show the diagonals here, but you see how they come off the figure and say the length of this, they bring it down and say this length right here. Maybe, you know what? I'm going to grab a colored pencil. This length is this D1. And then let me grab this other color. This length would be considered the D2 or a diagonal 2. Same thing over here. I'm going to take my D2. See, it's the same as that length they put outside. So you're going to see this as kind of common practice that they're going to go and put the lengths on the outside for these diagonals. They might be inside, but expect to look for them on the outside. And then let's just, a couple of things. Let me give you a kite example. So I'm going to try my best to make a decent looking kite here. It's going to be kind of taller. There we go. Oh, that's not terrible. And let me put some markings so you know it's a kite. And remember, kites have consecutive sides that are congruent to each other. Kites have consecutive sides that are congruent to each other. Now, let me give you some measures here. I got 11 feet and I got 5 feet. And yes, those are meant to represent the two diagonals. So that formula to find the area of a rhombus or a kite, it's the same thing. You do half of the product of the diagonals. So what is this going to look like when I want you guys to find me the area of this? Times? So that's 55. Half of 55. Half $55 would be 27.5. So half of the product of the diagonals, and that's going to be for a kite or a rhombus. I just dropped a kite as an example. You'll see rhombuses as well. So good deal. We got that formula. Turn your page when you're ready to go on. All right, area of a regular polygon. Now, regular. What does regular mean again? Same sides and angles. All the angles and sides are the same, like a stop sign. Now, this formula is where this gets a little bit crazy. First of all, I want you guys to, what color was your apothem on the last part? My apothem was blue. I want to pick up the same color. And I want to go in the figure that's here, and I want to use that color on the little A there, because that's the apothem. This is going to be the one, and I'm going to go take my colored pencil, and everywhere I see the little A, I'm going to make it that color. That's going to be the one that you guys are going to struggle to like, okay, wait a minute, what was that apothem thing again? Now, what the formula is for the area of any regular polygon, the area is equal to half of the apothem times capital P. Well, capital P still is standing for perimeter. Capital P is still standing for perimeter. Now, perimeter, I want you guys to notice here, let me just take my pencil, that they replace capital P from one formula to the next with N times S. Area is 1/2 times the apothem times the perimeter. So they've replaced the apothem P with N times S because the number of sides times side length will get you the perimeter. That's what they're showing here. So our formula is going to be half of the apothem times how many sides there are and how long a side is. They're calling the side length S and the number of sides N. And you guys notice this S is sitting out here right now. There's your side length. So like the perimeter of this figure would be S plus S plus S plus S plus S plus S, or S times 6, because there's 6 sides to it. So let me just make an example out of the drawing that we have. For the hexagon, if the side length is 10 and the apothem is 8, what's the area? So let's put this stuff on the figure. Side length is 10, and I'm telling you the apothem in there is 8. So I'm just beefing up what we're looking at here to make an example out of it. Side length is 10 and the apothem is 8. And then I'm going to find the area using this formula up here. How about the perimeter? Before I even start writing stuff down, if one side of this is 10, how far, what's the length all the way around, the perimeter of the whole thing? It'd be 60 because it's 6-sided. You know, don't get stuck on the 6. You might have an octagon, you might have a 10-sided figure, but the perimeter depends on the number of sides. So the area is going to be equal to 1/2 times the apothem, which was 8. And then the perimeter is going to come from 10. Oops. Let me put the 6 first. 6 times 10. So you're going to have to go into your calculators for this. Actually, I think I could do it. What's half of 8? What's 4 times 60? Bigger. 240, yeah. So half of 8 would give us 4. Sit there with that 4. 6 times 10, 60. The area, that would be 240.
Oh, you gotta find the half. Oh.
Now, there's also something interesting going on here. If you guys notice here, we're breaking up this regular polygon into triangles. And just kind of follow along as I talk through this. If we're breaking this thing up into triangles, and I don't want you to shade out anything. Oh, I wanted yellow. I don't want you to shade out anything. I just want you to kind of get your brain around this because I think it'll help you remember the formula. How do we find the area of a single triangle, you guys? Single triangle. 1/2 times the base times the height. Check out this formula. There's a half. There's the base. There's the height. What does the 6 represent? Sure, it also represents that there's 6 triangles just like this. So this is basically your area formula for a triangle, 1/2 times the base and the height. That's telling us there's 6 triangles like that. Does that make sense-ish? One of these triangles would be 1/2 times 8 times 10, but there's 6 of them. So that perimeter piece gets into talking about how many triangles there are based on the number of sides. I'm going to stop the video here before we go into extra practice.